So I'm just going to stop talking for an hour and a half.
Okay, thank you. Thanks for having me. So this particular area of the syllabus, it's caused a lot of angst because for the first time NESA has actually thrown in statistics in a science course. And the type of statistics that we're actually talking about in this course is actually not even covered in the math syllabuses. Okay, so it's a fairly high level statistics, but don't freak out. Okay, it's not that difficult, at least hopefully. By the end of this session, you'll see what I mean when I say that it's not really difficult. A lot of it just comes down to you demonstrating that you know how to interpret the results of statistical tests. Okay, we're going to take whatever that the science that you've been learning in the other courses, the types of experiments that you've been doing in the other courses. We're going to take that knowledge into a specific type of data analysis. Okay, so I've put together this additional set of notes, and my plan for this session is to go through some of the theory behind it. Obviously, I can't go through all of the content that's required for this part of the syllabus, but I'll sort of gloss over some of the things, right? And then go through a couple of examples of how to use statistics to analyze data. And in doing so, hopefully highlight some of the strategies you can use in the exams. So why did NESA put this into the syllabus? Well, statistical analysis is now part and parcel of scientific research. You can't do research without some understanding of statistics. Okay. It's currently the 50th anniversary of the moon landing, right? And the amount of data that the Apollo 11 program generated could be stored on a single floppy disk. Okay, the floppy disk, which is before your generation, okay, was the device that was used to store data, 360K of data per disk, right? When I was working in research, my background is in genetics. I used to sequence DNA a lot, genome sequencing. The average size of data from a single eukaryotic genome generally goes into gigabytes. Okay? That amount of data that you get from a single genome sequence read, it's very, very difficult to analyze. So you need multiple computers. And generally you don't do a single sequence read. Okay, you sequence a genome multiple times. You know, DNA is double-stranded, so you sequence each strand, that's twice. Okay, and you do multiple times of that. And so there's a lot of data that comes from a single experiment. Okay, the Hubble telescope experiment generates terabytes of data. So does the LHC, the Large Hadron Collider. When we've got so much of data, we need to actually develop or use tools that gives us confidence that what we're looking at is real. And that's where statistics comes in. Okay? So statistics gives us confidence that our results are real. And that's essentially why we use statistics in science. We've got instrumentation coming in, and in the Investigating Science course, we talk a lot about the role of technology in science. With instrumentation, you get increased sensitivity, so the volume of information increases. So does the resolution of the data. So and that's the reason why we need to know about statistics. Unfortunately, it's thrown in in a Year 12 course, okay, without all the necessary lead up. If you do science, engineering, medicine type degrees at university, you will be exposed to a higher level of statistics. Okay, you'll learn a lot more about these, the same ideas that I'm going to be talking about, but at a much deeper level. Okay, so that in a nutshell is the reasons why we have statistics in this course. So has everyone got a copy of the handout? Okay, so I'm just essentially going to go through that handout, or at least most of it. So the statistics part appears in Module 3, and the expectation is when you're doing this in class that you'll be working with some data, okay, if that's in addition to the stuff that you might be producing in your research projects, that you'll be working with some data, and that you'll also be analyzing that data with some software, okay? The syllabus does not specifically describe a particular software that you need to use. So it doesn't matter exactly which type of software is used. There are many, many, many different types. Some that are like Excel, they're actually spreadsheets. They're not really statistical software. You have specific software for statistics like SPSS, Minitab, and R. And then there are a number of online software packages as well. So depending on the situation in your schools, feel free to use whatever software that's available and that's easy to use. Okay? So we're in Module 3, and in terms of the specific content area, we want the syllabus requires you to essentially understand mean, median, and standard deviation, and that's generally relatively easy and straightforward. You've also would have done this in maths. You need to understand terms like error, accuracy, precision, bias, and data cleansing. Okay, these are methods that are used in data analysis. Okay, and you need to be familiar with those sorts of terms. In terms of the statistical tools, and this is one that has that strange phrase, including but not limited to. At a minimum, you need to know what's a student's t-test, a chi-square test, and an f-test. At least to have used these sorts of tests in the classroom. Okay? I'll give you an overview of what these tests are. You don't need to know when to apply these tests. Okay, thank you so much. Thank you. No, that's all good. Thank you. You don't need to actually know, should I use an F-test for this particular analysis, or should I use a T-test? You don't need to know that. Okay? That requires a lot more a detailed understanding of statistics. But you do need to know what these tests are. Okay? You do need to know what an F-test is. You do need to know what a T-test is, etc. Okay? I'll tell you some of the basic principles behind those in just a tick. You need to know about Pearson's correlation coefficient. Okay? When you do a correlation analysis, okay, we do something called a Pearson's correlation coefficient. Most of us would have done it in one form or another. You need to know a little bit about it. Okay? And then it goes into things like correlation and causation. Okay? So once you know what correlation is, how do we then link it to causation, if causation exists? Okay, as Bill was mentioned earlier with Nick Cage's movies and the number of deaths. Okay, So there's correlation, but where does causation fit in? Okay, you need to know that. Okay, and then finally applying statistical tests, which is fairly obvious. All right, moving on to page 2 of your handout. Okay, what I've done here in this figure is to show you where all of those different elements mentioned in the syllabus, okay, actually how they relate to each other. So let me give you this overview. In statistics, okay, when we talk about statistical testing, we're essentially talking about 2 branches of statistical tests. Okay. On the left-hand side, we have descriptive. On the right-hand side, we have inferential. Okay. So if I were to skip down to the orange bits, see, mean, median, standard deviation, they're mentioned in the syllabus. They all fall under the category of descriptive statistics. Okay. And on this side, where we have F-test, students' t-test, and so on, they're all inferential. Why this distinction? Well, descriptive statistics essentially is used to describe data. Okay? So given any data, okay, you can use those tools like mean, median, standard deviation, etc., to describe it. So imagine if you have, say, Donald Bradman's batting record. The number of runs he scored per game. So you have a whole string of numbers in front of you, right? You can talk about the mean, the median, the standard deviations, etc. You want to talk about the house prices in Sydney. Mean, median, standard deviation. You want to talk about, say, blood pressures of people around the world. Mean, median, standard deviation. It just gives you an overview of the data. It's descriptive. Inferential tests allow us to make predictions and conclusions. Okay, so the F-test, the t-test, and so on can allow us to make conclusions about data. What does it mean? What is it telling us? How can we use that information further? Okay, that's what inferential, you infer something. Just going back to descriptive statistics, okay, we have 2 little branches here. So under descriptive statistics, you have measures of central tendency. That's just a fancy way of saying where is the center of your data. And that's what mean, median, and standard deviation allows us to find out. What's the center? Where's the midpoint? What's the average? And what's the spread? Okay. So again, if you want to look at, say, house prices in Sydney, you can go with mean. What's the average house price in Sydney? And that gives you the center value, right? The problem with means is that it's sensitive to outliers. So sometimes we use median. And very often in the news you'd hear the phrase, the median house price. Because that gives you a better indication of the center when there are outliers. And we have standard deviation. So you know the middle. How far does the data spread from the middle? That's standard deviation. So all of that is used to describe data. Another thing that we use in descriptive statistics is something called distributions. And for the science extension course, You just need to know one type of distribution, that's called the normal distribution. Okay, so the normal distribution, and I've got a few descriptors below, it's basically the bell curve. If you do statistics at university, you'll learn a lot more about binomial distributions, Poisson distributions, etc., etc. But for science extension, we only need to know one, the normal curve, the normal distribution, the bell curve, the Gaussian distribution. They all refer to the same thing, okay? Under inferential, we've got two types of inferential statistical tools. So we use inferential statistics either to establish relationships, in other words, find correlations. One of the things that you're expected to do in science extension is to identify patterns and trends in data. So given a data set, you're expected to find patterns and trends. Correlation is one of those tools. Okay, so that's the Pearson's correlation. The other thing that we use inferential statistics for is to make comparisons. So you've got control versus treatment. You've got two groups. Compare the two. Right? That's where you would use all of these things. Okay? So if you're going to compare two or more data sets, okay, we use these tools. If you simply want to find correlation or relationships, you use the correlation coefficient. So that gives you an overview of what all of these terms are that are described in the syllabus. Okay, so hopefully that sort of simplifies, what these tests are and what they're used for. As I mentioned, you would need to use some software in the classroom. Excel is probably the easiest to use if you're using Microsoft products. And if you do that, you've got to make sure that this add-in analysis tool pack is activated. It's free, but you actually need to activate it. And that gives you access to most of the tests that are described in the syllabus. If you use Google Spreadsheets, they have an equivalent add-in, but unfortunately the commands are different. Okay. There isn't, as far as I know, if you're using any of the other operating systems like Linux and so on, there isn't any equivalent. You'll have to use online software tools. Okay. So that's just the summary of Excel if you're using Excel. And the other funny thing about Excel is if you are using Excel, the analysis tool pack for the Office 2016 and above is much better than the one that for the Office 2011 or 2013. Okay, so if you do have the opportunity to update it, do update it, because the analysis tool pack for the 2016 and later has got more functions in it. But that may be beyond your control though. This part is a little heavy because I'm going through the background bit. But then when we do the problem solving, it'll all sort of fall into place. So for central tendency, I've defined mean and median. That's again fairly obvious. The syllabus talks about standard deviation, but you actually also need to know a related one called variance. again, I don't know who put this together in the syllabus, but you know where it says F-test? F-test is a test of variance. So you actually need to know what variance is. Okay? So I've defined variance and standard deviation there. Okay, they're both listed there. But both variance and standard deviation are very, very, very similar. Okay, so imagine a bell curve, okay, and imagine the center point, right? And when we talk about the spread of the data from the center point, we use the terms variance and standard deviation. There's a mathematical difference between them, but don't worry about it. So once again, both variance and standard deviation tell us how much the data spreads from the center. Okay, they're very closely related, and if you use that analysis tool pack, it'll always tell you variance and standard deviation. Okay, you just need to know those terms. Okay, in the exam, you're not expected to actually calculate any of these things. Okay, but you may be given some results of a statistical test, and asked to interpret it. Okay, as in the sample exam question. Any questions on central tendencies? So the descriptive stats, mean, median, standard deviation. It's relatively simple concepts, right? All good? Okay. The next thing you need to know for statistics is the type of data that you're dealing with. Again, for year 12, for the science extension course, we just need to know that data can be either qualitative or quantitative. Okay, so qualitative data would be things like, say, the color of our eyes. Okay, so it's going to be blue, green, brown, for example. Okay, so blue, green, and brown would represent qualitative data. Quantitative data, as the name suggests, involves measurement, involves numbers. Okay, the reason why you need to know the data is that the type of data determines the type of statistical test that will be used. In the syllabus, we're talking about the chi-square test, the t-test, and the f-test. They all use different types of data. Okay, so you essentially need to know that there are two types of data, qualitative and quantitative. And where does it all fit in? Well, if I could just scroll down, okay, to this figure on page, this is on page 4, okay, I'll come back to this figure a bit in just a little while, okay. See the very first branch in this figure when we're talking about, so this figure just basically tells us the relationship between the different types of statistical tests. Okay, they're all described in the syllabus. So all I've done is given you a visual overview of these tests. But look at the very first branch there, okay, that says quantitative or categorical. Categorical is another term that means qualitative. So depending on the type of data, it actually determines the type of statistical test you would use. Okay, so that's the reason why you need to know about the type of data you're dealing with. Let me go back to this. For us as science students, the only reason why we are studying statistics is so that we can relate it to the experiments that we are conducting. And that's really important for you for the HSC. Because all of those statistics bits will ask you to relate it back to the underlying science. So we're not learning statistics for the mathematics, for the other aspects of why we use statistics. You need to know statistics because of hypothesis testing. Okay, so always related back to scientific hypothesis. I want to go back to Module 1. Okay, and when Bill was talking about it earlier, he talked about falsification. So Sir Karl Popper, he was quite an influential thinker, he's a philosopher, and he essentially said that you can't prove anything in science. You can't prove that something is true in science. What you can do is identify what is not true and discard those things. So you get closer to the truth by discarding whatever is false. Is everyone okay with that idea? Because that's the basis of hypothesis testing. Okay? So we identify and discard whatever is not true to get to the truth. Double negative. Okay? And hypothesis testing has been designed along those lines. Okay? So the other thing in Module 1 is that all of science, all of modern science, generally falls into one of two categories. It's either inductive or deductive. In deductive science, right, you have some established scientific truth. For example, hemophilia runs in families. And if a condition runs in families, then it's very likely that there is a genetic basis for it. If there is a genetic basis for it, then there must be a gene responsible for that condition. So let's go and look for that gene. That's deductive thinking. Okay? Hypothesis testing is related to deductive thinking. That's the reason why we have these kinds of philosophies of behind scientific thinking in Module 1, because it kind of links to everything else in Modules 2, 3, and 4. The other type of reasoning in science, okay, inductive thinking, it's more like, hey, let's sequence the genome of an organism and discover what's encoded in it. Let's point the Hubble telescope to one part of the universe and see what it reveals. We don't know, we have no prior knowledge, or we might have some prior knowledge, but it's more of a discovery process. Okay? So we have these two contrasting lines of thinking in science. One is more discovery-oriented. Hey, we are an explorer. Let's go out there. Let's go and discover something. Okay, it's sort of a difficult branch of science. The other type is hypothesis testing. Okay, where you use logical reasoning. You start with an established scientific concept, and then you slowly reason your way through, and then you develop your experiment. And that's where we have hypothesis testing. For hypothesis testing, you need to know the meanings of all of these. I won't go through everything. I won't go through all of this. Have a read of this when you get a moment. But for hypothesis testing, you need 3 hypotheses. The scientific hypothesis, which is the hypothesis for the investigation. You need something called a null hypothesis, and you need something called an alternate hypothesis. Okay? You need to know these 3 things. So we have a scientific hypothesis, right? Because of Sir Karl Popper's falsification, we need a null hypothesis. The null hypothesis opposes the scientific hypothesis. It says that whatever you're investigating is not true. That's the null hypothesis. Then we have the alternate hypothesis, which is the opposite of the null hypothesis. See, we kind of make life difficult, right? It's a double negative. So we might say, physiotherapy improves recovery time after knee surgery. That's a scientific hypothesis. A null hypothesis would be that there would be no improvement in recovery times after, with physiotherapy after surgery. Do you see the relationship between the null hypothesis and the scientific hypothesis? It's important that you understand that. Okay? So that is the key thing about statistical testing. You need to develop a null hypothesis. The alternate hypothesis is actually very similar to the scientific hypothesis, because by the time you develop the alternate hypothesis, it's a double negative. It goes back. You need to know these three things. The p-value, oops, missed that. P-value, confidence interval, and alpha value. These are things that statisticians use all the time. And I'm going to describe it in a very non-statistical way. Okay? Confidence interval. Oops, let me remove that thing. I'm going to start with confidence interval. And I'm going to be very statistically incorrect when I describe this. How confident do you want to be of your result? Assuming that you cannot be 100% confident. So you're going to do an experiment, control versus treatment, right? You get your results. How confident do you want to be of your experiment? Is 99% your accepted criteria? Is it 95%? Is it 70%? Now, when scientists do these experiments, they generally have a pretty good idea about the confidence interval, because they use a lot of pre-existing information, other information, they use that. And they come up with a confidence interval. In most cases, and again, for reasons that we are not sure why, most people say 95% confidence is acceptable. Okay? 95% is kind of like the golden rule. Most people accept that. So in your exam questions, if they don't specifically talk about it, assume that the confidence interval is 95%. Okay? That's like a golden rule. Now, the alpha value. Alpha value is also called the significance value. It's also called the critical value. You might see different terms used by different authors. And this is another stupid problem in statistics. You find that there are all these terms that are being used, but they all generally refer to very similar things. So the alpha value is the threshold, what we called the cutoff. So, and it's related to the confidence interval. Okay, So the alpha value is essentially, okay, this bit here, it is 1 minus the confidence interval. So if you say that we'll go with 95%, so 95% in decimals is 0.95, right? So then the alpha value is 1 minus 0.95, which is 0.05. Is everyone okay with that? If I am going to be 90% confident of my results, if I'm okay with 90% confidence level, right? So 90% is 0.9. Then my alpha value would be 1 minus 0.9, which is 0.1. If I'm going to be 70% confident of my result, 70% is 0.7. Then my alpha value will be 1 minus 0.7, okay, which is 0.3. You get the drift? Okay? The reason why the alpha value is important is because when you do a statistical test like a t-test or a f-test or something like that, right at the bottom you get something called a p-value. Okay? P-value here, again, I'm going to be statistically incorrect, okay, in terms of these definitions. A p-value here is the probability that the null hypothesis is true. So you know you've got the null hypothesis. What is the probability that it is true? The statistical test itself will give you a p-value. So p for probability. So you need to know all of these little bits when you perform a statistical test. Okay? When you're doing this in the classroom, okay, when you're doing some data analysis, okay, look out for these terms. P-value, confidence interval, and the alpha values. Okay? All statistical tests, inferential statistical tests, require them. Because otherwise, the statistical test itself will not make sense. I will show you how this is going to be used in just a sec. Okay? So, once again, these three things, okay, p-value, confidence interval, and alpha value, they're kind of all related to each other, but you need to know what they mean. I want to talk about something called tails. And this is going to come up when you do F-test and T-test. You need to understand this term that we call tails. Okay? A statistical test is either one-tailed, okay, shown here, one-tailed, or two-tailed. This table here explains this. Let's say your hypothesis is treatment is greater than control. You're looking for 1 point of difference, and we call that one-tailed. Let's say your hypothesis is treatment is less than control. You're looking at 1 point of difference, and so it's called one-tailed. But let's say your hypothesis says treatment is different to control. You're not specifying whether it's greater than or less than. That type of hypothesis will be two-tailed. Okay? Is that sort of making sense? The reason why you need to know this, tails, is because if I were to scroll down to this is on page 5 at the top. This is the result of a t-test. You will get something like this. You may get something like this in your exams. A t-test was performed, and here's the result. You see how the P here says one-tailed and two-tailed? The statistical tests will not distinguish it for you. You have to distinguish it. Which p-value will you use? In this particular case, it just so happens that they're identical. So you can use any one. But sometimes the one-tail and two-tail will give you different p-values. And you just need to know which one to use. And always go back to the hypothesis. Okay? Is the hypothesis specific? Does it say that 1 is greater than or less than? In which case, it's a one-tail. If it is not specific, if it just says treatment is different to control, then it's two-tailed. Okay? This is one thing that you just need to be aware, because in the science extension exam, very often, at least a lot of the questions that I've looked at, you will see the output of a statistical test. Okay? And you just have to make sure that you use the right p-value. Okay? And this is the reason why you need to know a little bit about the tails. Sorry, I know it's a little heavy. It's like all these terminologies that we've got to talk about, and in such a short space of time. But I'm just sort of highlighting the essential bits. Okay. Okay. Can I go to the middle of page 3? The middle, so in the middle of this page, okay, those 7 steps tells you essentially how to do a statistical test, what you need to do. Okay, so we'll start with step 1. Okay, define the null hypothesis and the alternate hypothesis. Again, straightforward. You know your scientific hypothesis, just use that to derive the null hypothesis and the alternate hypothesis. Decide whether it's going to be a one-tailed or two-tailed test. It's not always applicable, but for t-test and f-test, you need to know whether it's one-tailed or two-tailed. Again, go back to your hypothesis. Okay? Identify the confidence interval and the alpha value. That should be alpha, not A. Number 3. So remember I said the golden rule, 95% or alpha of 0.05. Okay? If it's not otherwise indicated in the question, just assume that alpha is going to be 0.05. And then do the statistical test. So here in step 4, whatever the test might be, just go ahead and do it. Once you've done that, once you've completed your statistical test, at the end of it, you'll get a p-value. Compare the p-value with the alpha value. So compare p with A. Okay, this is the part that you will be expected to do in the exam. Okay, so this is the part where you need to analyze the P and the A.
So you know in step 2, you said decide the technical and number.
Yep.
Which hypothesis are you talking about?
The scientific hypothesis.
What's the difference between the alternate hypothesis and the scientific hypothesis?
They're very similar. They're very similar. The reason why we do it this way is because you've got your scientific hypothesis at the start, and then we leave it one side. You don't touch the scientific hypothesis during the statistics. You only play with the null and the alternate hypothesis. Question?
Just in your last step there, where you said you can accept a null, can you accept a null or can you just fail to reject it? Because then it comes back to spurious inputs, the bias.
Yes. I'll put it in a very simple way. Yeah, it's a very good question. When you actually do statistics at uni, you'll get a slightly different answer to what I'm going to describe. You will, in essence, it's either you reject or not reject the null hypothesis, if that's kind of making sense. Okay, I'll give you an example in just a sec to try and clarify that. Okay, so in step 5, you're comparing P with A. If P is less than A, in this case I've used 0.05, the golden rule. Okay, you reject the null hypothesis. So P less than A, reject null hypothesis. P greater than A, you accept the null hypothesis. And I think I've kind of put it in a table for you. P less than A, reject the null hypothesis. P greater than A, you accept the null hypothesis. You're only working with null hypothesis here. That's the bit that's actually being tested. Okay, you ignore everything else. Okay, so you've got the p-value from the statistical test, compare that with the A. P versus A, and that's all that you have to do. And this is what I mean by when you ignore the details, the statistical testing process is actually relatively straightforward.
When do you use the alternate hypothesis?
When the null hypothesis is rejected. Okay, and I'll come back to that once again with the example or the figure on the next page. Yeah?
So in the conclusion, right, you know you have to refer back to your hypothesis, right?
Yes.
Do you refer back to your alternate hypothesis or do you refer back to your scientific hypothesis?
Scientific hypothesis. So after you've completed all of your statistical tests, so whether you accept or reject your null hypothesis, you have to always relate it back to your scientific hypothesis. Again, we'll try and answer a question related to that. So the steps here, once again, starting with the scientific hypothesis at the top, right? You then create a pair of hypotheses for the statistical test, the null and the alternate hypothesis. Okay, all of this is simply based on the wording of the scientific hypothesis. You then perform the statistical test on the null hypothesis. Right? So you've got your data, you perform your t-test or f-test or chi-squared test, and at the end of it, you get a p-value. Compare the p-value with your a-value, whatever has been decided. Okay? If p is less than 0.05, reject the null hypothesis. If you reject the null hypothesis, just follow that thing, you accept the alternate hypothesis. If you accept the alternate hypothesis, that means it supports your original scientific hypothesis. See what a complicated world Karl Popper has created? But it's a very powerful mechanism though. It's a very, very powerful way for us to determine how confident we can be of our scientific results. In many papers, if you don't actually have these sorts of validation, the journals will not accept the papers for publication. If P is equal to or greater than 0.05, okay, then you accept the null hypothesis and you reject the alternate hypothesis. If you reject the alternate hypothesis, then it means that the scientific hypothesis is not supported. Deductive thinking. Okay? That's what hypothesis testing is all about. All of these processes you need to be familiar with. You're not going to be actually be doing a statistical test in the science extension exam. You actually need to understand that process. The reason for this is when you read those questions, you need to actually visualize the experiment itself. You need to form a mental picture of what the experimenters are actually doing. Okay? So here on this page, that coming back to this figure, that gives you an overview of the different types of statistical tests in the science extension syllabus. If you're working with categorical data, okay, the type of test you would use is a chi-square test. So that's going towards the right. Okay? So if you're working with categorical data, you're going to be using the chi-square test. Flip that argument. If you're looking at a chi-square test, that data that you're looking at is categorical or qualitative. On the other hand, if you're working with quantitative data, remember I said you can do one of two things. You can try and establish relationships, in which case you're going to be using the Pearson correlation coefficient, or you're going to compare data sets, control versus treatment. What can you compare? You can compare variance, in which case you'd be using the F-test. If you're going to compare the means of the data set, you will use t-tests. Okay? That is a very, very simplified overview of the tests described in the science extension syllabus. Once again, for inferential statistics, if you're working with qualitative data, it's going to be chi-squared. If you're working with quantitative data, well, what do you want to do with the quantitative data? If you want to establish relationships, okay, is there a relationship between the independent and dependent variable? You would use the correlation test. If, on the other hand, you want to compare between two or more data sets, what do you actually want to compare? Variance? Use the F-test. Means? Use the t-test. Okay? Just a very simplified overview of the different types of statistical tests described in the syllabus. There is a lot more to this. Okay? Once again, if you do this at universities, you have things like tests of normality, the power of testing, etc., that needs to be applied. Okay? Don't worry about those things. All you need to know is what are these tests and what are they used for. So if you get a question like, hey, they did a t-test, what were they comparing? Well, they were comparing the means between the data set. If someone were to say, what type of data was used if the researchers were using a chi-square test? They were using qualitative data. Okay? Make sure you understand the rationale. Okay? You're not expected to do a statistical test in the exam. You need to know how to interpret it. One final little bit about theory. It's got to do with uncertainty and error. I think in the physics course you do this fair bit. Am I right, Bill?
Not really.
Not a lot? Okay. I know in investigating science we do talk about the types of errors. Okay.
Only at a very, very basic.
Very basic level, yeah. Okay, systematic and random errors. Okay. You also need to know a little bit about these sorts of things. Okay. These are types of errors and uncertainty. If you go to the Department of Education website, and I'm going to take you through multiple clicks because nothing is easy with our websites. Go into teaching and learning, go into curriculum, go into key learning areas. I will actually put this resource, I'll send it to Bill so that he puts it up on your site. Go into science. What's this, a fourth click? We're going into stage 6. Right down at the bottom here for under stage 6 you have resources. It's like the 8th click. I tell you, nothing is easy with us. You have these two files here. Those two resources essentially talk about the definitions of accuracy, reliability, and validity. NESA has checked, have gone through this as well. The abridged version, if I can download it to the desktop. And then the full version. Because in science extension they actually introduced the word precision. It's not there in the glossaries for the other subject areas. We've put together a basic definition, okay, and also synonyms and additional notes about these definitions. This is largely because of the science extension course. You're expected to be sort of looking at the literature, looking at reading some of these articles and so on. And when you look at the scientific literature, they tend to use slightly different terms depending on the discipline. So we've put in precision here, right? And precision is sometimes called internal reliability. Okay, and then you have the traditional reliability, and then you have validity. Okay, so that's this. It's a one-page summary. I've also put together the other one, which is monstrous. Okay, it has more detailed description of accuracy, reliability, precision, validity, and so on. But also, oops, here, I've put together a discussion of causality, cause and effect, okay, errors of measurement, and uncertainties. Okay, so if when you get some time, not that you're going to have a lot of time, but there is a lot of these resources up there. We've put together these sorts of information. Okay? And that will help you with making sure that you understand what errors and uncertainty and things like that are. Okay, let's get back to our stuff. You might have seen some of these examples in your classroom, but if you have, then treat this as a revision. Here's an example of a scientific investigation that involves statistical analysis. Just have a read of it. Just take a couple of minutes to have a read of it. Sorry, there's a typo. So this is a relatively straightforward experiment. In the exam, when you're given a description of an investigation, try and visualize what the experimenter is trying to do. Because if you form a good mental model, it's going to help you with the interpretation of the statistical data. So you're told here that this biologist is studying the effect of a plant growth formulation. And you're told that there are two iris varieties that are being tested. Iris virginica and Iris centosa. The biologist believes that the formulation improves the growth of the virginica, but not the centosa. As you're reading through this, try and develop the hypothesis. It is one of the things that we're going to do, but as you're reading through the stimulus text, try and form the hypothesis. What is the experimenter actually trying to do? To test that theory, the experimenter has set up two groups of plants. Group 1 contains 35 virginica plants, and Group 2 contains 38 centosa plants. So equal amounts of formulation was applied to both plants, and the length of the leaves was used as an indicator of growth. Now comes the statistical bit. You're told to assume that the alpha value is 0.05. Okay? You're also told that the biologist performed a t-test. So given this particular set of information, you're then asked to analyze the results. Okay? There are two parts to the result, or two tables given to you. On the left-hand side, it says that's the data summary. And on the right-hand side, you've got the results of the t-test. Okay? The data summary shows two columns, A and B. And just in the preceding page, I've said A is virginica and B is centosa. Based on all of that information, what's the hypothesis? Any suggestions? What might be a good hypothesis? A reasonable hypothesis? Anyone? Feel free to discuss what might be a decent, good hypothesis for testing. I'll also let you know up front that there is more than one possible answer to this. Any thoughts? Any suggestions?
To determine the effect of the Lympha and growth formulation on the two specific plant series, Iris virginica and Iris setosa.
So, you said to, sorry, could you repeat the first part? To determine the effects of the formulation on the two Iris varieties, virginica and setosa. Any other suggestions?
Like the plant growth formulation has a higher effect on the plant plants on virginica than setosa.
Then setosa, thank you. Any others? What's the purpose of a hypothesis? Anyone? Any thoughts? What's the purpose of a hypothesis? Why do we need a hypothesis for an investigation? It's a prediction of possible outcomes. So that means that the predicted outcomes must be indicated in your hypothesis statement. Okay? You need to indicate a predicted outcome in your hypothesis statement. That's the difference between hypothesis and an aim. Okay? Don't confuse the two. A hypothesis must have a predicted outcome. So, let me go. So I've got two possible statements there. Okay? In the first one, in the first one, I've just said the plant formulation improves the length. Okay guys, listen up. The plant formulation improves the length of I. virginica compared to I. centosa. Okay. Notice that it is not as specific as the second one, that the leaf lengths of I. virginica will be greater than or longer than I. centosa in the presence of the formulation. To have a good quality hypothesis, make sure that both the independent and dependent variables are indicated in your hypothesis statement. Okay? So the formulation is the independent variable, the leaf length is going to be your dependent variable. Make sure that both of those phrases appear in your hypothesis statement. So the second statement here, or something along the lines of that second statement, is a decent hypothesis to work with because you've indicated the independent and dependent variables and you've made a predictive statement. Right? Given that, let's look at the second red, the sentence in red. Is that going to be a one-tailed or two-tailed? One-tailed, thank you. Because it's greater than. We are being very specific about it. So it's going to be one-tailed. What could be a null hypothesis? Let me just actually now temporarily what would be a null hypothesis? Thank you. So in creating the null hypothesis, we are kind of opposing the scientific hypothesis. So I've put down two sort of similar statements, okay? One in a positive tone and one in a negative tone. Yes?
Would you include like the leaf length of I. virginica will be the same as or less than that of I. centosa?
No, we're just opposing the scientific hypothesis. So you have to look at the wording of the scientific hypothesis.
The scientific hypothesis says that the leaf length will be greater. So that.
And all you're saying is that that's not true. No, you're not stating. So if it says greater than, you're not stating it's going to be less than.
Yeah. So the opposite of that, wouldn't it be equal?
It's not greater than. You don't know that though. You don't know that it's going to be less than. All you're saying is, in the scientific hypothesis, you said virginica is going to be longer than centosa. And the null hypothesis says that's not true. Okay? So do you understand the subtle difference between the two?
Because like saying that it's not
the thing is that when you say it's going to be less than, that's a different hypothesis.
It could be the same as or less than.
It could be, but in the null hypothesis, you can only test one of the two. Okay? And you have to pick the one that is as close as possible to the scientific hypothesis, but it kind of doesn't agree with it. Okay? Sorry, did you have a question? Okay, good. Any questions on the null hypothesis? Yeah?
Could you use that as the alternative, or is that too different?
It's too different. I wouldn't say that for the null hypothesis, I wouldn't say that it is less than. All I'm saying is that the scientific hypothesis is not true. Remember, the principle of falsification is not the principle of opposition. Okay? So we're not going the exact opposite term. We're not using the antonym here. Okay? All we are saying is that whatever is stated in the scientific hypothesis is not true, and we're going to test that. Okay? So for the alternate hypothesis, we can just go back to the scientific hypothesis, because it's going to be almost identical. Okay? And just in the interest of time, I'm just going to copy and paste that. So we've done the initial parts of the statistical analysis. Okay, this is the preparation. We've developed the null and alternate hypothesis. Okay, what we now have to do, and this is I guess the crucial part for you in the exam, would be to analyze the result. Is it true? And if you look at the sample exam question on the statistics bit for science extension, it says to justify your answer. Okay, so in terms of Bloom's taxonomy, we are looking at a very high order level of reasoning. So what NESA is expecting you to do in the HSC exam, for the science extension exam, is to actually use all of that information, the information about the experiment itself, as well as the result, to justify your answer. We need to go back to the results to write down, to develop our conclusion. Remember, our hypothesis is that the formulation improves or increases the length of Virginica leaves compared to Centosa. That is going to be our reference point. Okay? We are always going to come back to that statement, that Virginica leaves are going to be longer than Centosa. Let's go back to the results. What do the results say? See this bit here? And I'm sorry, it may not be very clear in your printout, but see that column that says mean? I'll try and zoom in a bit. See that first table on the left, and where it says mean, okay? And remember, A is Virginica and B is Centosa. Look at the mean lengths. Is Virginica longer or greater than Centosa? Is A greater than B? So that's going to be the first part of your conclusion. Okay? The results indicate that the average or mean length of Iris virginica leaves is greater than the length of the Sentosa leaves. Now HSC will, when the markers are marking the exam, they will give you more marks if you actually use the information that's provided to you. Information in the stimulus text. So let's go back. So that says 5 point, I'm just going to round it off to 5.5. So you see how we are justifying our statements with information that's provided in the stimulus text. So don't just say that the results indicate that Virginica is longer than Sentosa. Use the information in the question itself to support your statements. Remember, we are justifying evidence-based reasoning. Okay? So you need to make sure that you use the information that's provided in the text. Sorry? Yes. Yes. Yeah? No, I don't think we have time.
Because if you want some more time, what am I thinking? Maybe have a lunch break now.
Okay, after this question?
After this question, yeah.
Yeah, absolutely, absolutely. Okay. Does it say? No, it says, sorry, yes, 1.5. Yeah, sorry. So we've done the first part of our conclusion. We've used the results to kind of say, hey, the hypothesis is supported, right? So the results indicates that the hypothesis is supported. But now we need to weave in the other part of our results, where we're going to talk about the statistical analysis. So what can we say about the statistics here? Let me scroll up. Remember, you need to focus on one part of it, the p-values, right? We already said that this is a one-tailed test. In reality, it doesn't matter. They're both identical numbers, right? So we know that the p-value we're looking at is 0.001 or less. So what can we say about the results of the t-test? Should we accept or reject the null hypothesis? We reject. Okay, so Okay, so now we come in with the last part of your justification. So we are saying that the t-test indicates that because p is less than alpha, we're going to reject the null hypothesis. And in other words, that the scientific hypothesis is statistically significant. Or, going back to the wordings of our scientific hypothesis, that the difference in leaf lengths is statistically significant. Therefore, there's your concluding statement for a justify sentence. Oh, sorry, a justify verb. Okay? That's the sort of arguments that you need to string together to compose your answer. No, not at all. Okay? Is everyone okay with this? So you see, the theory part of it is fairly dense and heavy, but in terms of applying it, it's actually relatively straightforward. As long as you know how to develop your hypotheses, the scientific, the null, and the alternate hypothesis, as long as you understand the role of the confidence interval, the alpha value, and the p-value, you can usually analyze the results of any statistical study quite effectively. Okay? Should we?
So Shyam's going to come back after lunch and give us a few more examples.
Okay, so just to give you another example, just to highlight the common features of statistical testing. Okay, so here's another question that is looking. So question 2, sorry, my page numbering will change because I've been typing in into this document. So a student wants to determine if there was a correlation between nasal lengths and nasal widths of kangaroos. And this is an experiment to look at adaptation to hot, dry weather. So what the student did was essentially to go out into the field and measure these dimensions, and then came back to the lab to conduct a statistical test. You're told that the type of test here is a Pearson's correlation test. So that automatically should tell you that the researcher is trying to establish a relationship. Okay? So once again, a Pearson's test or Pearson's correlation test is a test to establish the relationship, if a correlation exists between the independent and dependent variable. You're also told that the alpha value for this particular statistical test is 0.05. Okay? So you're given those basic or essential information. You're then given the results. Once again, the results, well, you need to analyze the results, but there are certain things that are more important than others. So in this results table, you can see that in the top part, or the top table here, you're given the X and Y. You're told that X is nasal length, Y is nasal width. Okay, that's just up here. Okay, you're given the mean, variance, standard deviation, and standard error. Now, one of the reasons why I put this up is sometimes you may be given the outputs that contain information that may not make sense to you. So in the science extension course, we don't talk about standard errors. So we don't talk about standard errors of measurement. We only talk about standard deviation. So standard deviation and standard errors are two different things. So you have to essentially ignore those bits. Okay? So you know about mean, you know about variance, you know about standard deviation, but you don't really know much about standard error. So ignore that. That means that you don't need to use that information unless you know about standard errors. If you want to use it, well and good. But if you don't know about it, leave it out. It's okay. There's still a lot of information provided in those tables for you to make a reasoned argument. You're then given in the lower table a whole bunch of other bits and pieces of information. Again, there will be things that you know, and there will be things that you're not familiar with. Okay? For Pearson's correlation, okay, the R-squared value is important. See this bit here, R-squared. Okay. R-squared is important. Okay. R-squared simply indicates the degree of correlation, okay, between the independent and dependent variable. It goes from -1 to +1. Okay, so the R-squared value, actually R-squared goes from 0 to 1. So let me just write down here. So the second part of that bit, R squared ranges from 0 to 1. 0 indicates no correlation, and 1 indicates 100% correlation. Okay? So that's essentially what the R squared value says. So if you look at this result, see just that column that says R squared, it says 0.7769. So that means there is a 77.69% correlation between the independent and dependent variable. That's a fairly strong correlation. Okay? That's how we interpret correlation. Okay? Is everyone okay with that so far? Okay, so whenever you talk about correlation, look at the R squared value. Okay? I don't have time to talk about R at this stage. Okay, we'll just focus on R squared. So R squared ranges from 0 to 1. 0 indicates no correlation. 1 indicates perfect correlation, 100% correlation. Okay? That's how we interpret it. So 70, in this case 77.69 or 0.7769 indicates a fairly strong correlation. Okay. Now, we can ignore slope, we can ignore y-intercept, we can ignore the standard error of estimate. Ignore all of that. But in the bottom part, we have the other critical piece of information, the p-value. Okay? Now, and here's the one other confusing thing about statistical tests. A lot depends on the scientific hypothesis, right? So the scientific hypothesis, the wording of the scientific hypothesis is really important. Now these sorts of questions are sort of vague. You can actually derive more than one valid hypothesis for each of these questions. Okay, so don't worry too much about the exact wording just for today. Okay, I'm just showing you the process of how you would answer questions using statistical data. Okay. We are looking for correlation. So what would be a decent hypothesis? Let me scroll down to the question stimulus. What would be a decent question, a decent hypothesis? Yeah? Okay, so that there is a correlation between nasal lengths and nasal widths. Can we be a little bit more specific? Remember, we're trying to make a prediction.
There's a grade.
So what are we actually correlating here? So what are we predicting? Yeah.
One is like inversely proportional to the other.
Exactly. So as nasal lengths increase, that the nasal width would also increase. So that's the sort of specificity we are looking for. Okay, you're trying to make a prediction here. Okay, as science extension students, we are trying to create a really good working hypothesis here. Okay, and that hypothesis is going to indicate how these two variables are going to behave. We're going to say that we are going to make a correlation, that the nasal length is correlated with the nasal width because as nasal lengths increase, nasal widths will increase. That's the correlation. We're being quite specific about it. Yep?
But couldn't you have two different types? Couldn't you have as nasal length increases, nasal length decreases?
You could, but you're just testing a...
Would we need that?
Yes, absolutely. Okay? Like I said, these questions are slightly vague. You could come up with more than one hypothesis. Okay? So let's in this particular instance, let's write down this hypothesis. The important thing about hypothesis is that we have to make a prediction of an outcome. Okay? And that's how a hypothesis differs from the aim of an experiment. Okay? The aim basically is an overview statement, but a hypothesis must include a prediction. Okay? Try and make sure that the independent and dependent variables are indicated in your hypothesis statement. That's a good quality hypothesis statement. Now, can you just cancel out this question, please? We'll ignore the one-tailed or two-tailed. Just in the interest of time, I just want to go through the other bits. So now that we say that the nasal lengths correlate with nasal widths, that as one increases, the other will increase, the null hypothesis simply states that that is not true. Okay? The nasal lengths will not increase proportionately with nasal width. Okay? So, what can we conclude? To indicate whether there's correlation, you need to use the information that's provided in the stimulus text, yeah? You can reject the null hypothesis. Before we do that, can we say something about the correlation?
It's great. It's a great correlation.
Yep, so there's good positive correlation between nasal lengths and nasal widths. So everyone agree? What data will you use to support that statement? R squared. Thank you. So you make sure that the R squared value appears in your response. Okay? Sorry. Is there a question? Oh, sorry.
Do you have to know that the correlation is relatively strong, or would you just say a positive correlation?
A positive correlation. So generally speaking, if it's above 0.5, it's considered to be a strong, a reasonably strong correlation. Okay? So that's the first part of the conclusion. The results indicate that nasal lengths correlate with nasal widths because the R squared value is 0.7769. Okay, so we're using the information that's provided to us. Now we include the results of the statistical test. Okay, we're going to reject the null hypothesis because given that the alpha value is 0.05, P is less than 0.05, so exactly what we did earlier. We used the same sort of approach. We use that information, we put it together and say that because P is less than 0.05, we would reject the null hypothesis and accept the alternate hypothesis. Therefore, the results indicate that the correlation between nasal length and nasal width is statistically significant. Okay, give you a sec to think about that. So we first say that because P is less than alpha, if we reject the null hypothesis and accept the alternate hypothesis, therefore, the correlation between nasal length and nasal width is statistically significant. Okay, so we've already said that there is a correlation, and now we're saying that the correlation is statistically significant. Is that okay with everyone? Now, you don't have this particular question in front of you right now, but I'll give it to Bill to put it up. This is a chi-squared test, right? In this chi-squared test, a psychologist is looking at the relationship between personality, introverted or extroverted, and color preference. Notice that both the independent and dependent variables are qualitative data. So introverted or extroverted personality types. And then color preference, we've got 4 colors there. They're all qualitative data. So for qualitative data, we use what type of test? Chi-squared. Thank you. So this is the results of the chi-squared test. And once again, we do exactly the same thing. We would go through the process of identifying the scientific hypothesis. We go through the process of setting up the null and alternate hypothesis, and then compare P with alpha. In this question, for example, it says, assume that alpha is 0.05. So we are told that P is less than 0.0001. Reject the null hypothesis, accept the alternate hypothesis. In other words, the scientific hypothesis is supported. Do you get that thinking process? It applies to all inferential statistics. No matter what it is, whether it's a chi-square test, t-test, f-test, whatever it is, you use the same approach. Look at the results. Does it support the hypothesis? Then use the statistical output to say whether it is significant or not. Okay? Is everyone okay with that so far? One last thing before I finish my session. Again, you don't have this in front of you, but I'll give it to Bill, once again, the relationship between cause and effect. Okay, the syllabus says that you need to understand the difference between cause and effect as well as correlation. So with establishing causality, so you know when you do the Pearson test, you establish correlation. So we said that nasal length is correlated with nasal width. That's just correlation. It's not cause and effect. You haven't established the reasons for those correlations yet. What I'm trying to say with this, okay, this outline here, okay, I won't go through it in detail now, but essentially, cause must be closely related with effect if you're trying to establish causality. So, the first point here, cause must happen before effect. Okay, does that sort of make sense? Okay, cause must happen before effect. If in your investigations, if the effect happens before the cause, then you cannot establish causality. Okay, the second point, if the cause varies, the effect has to vary. Okay, that's how you establish causality. If one varies, the other has to vary. If the nasal length increases, nasal width has to increase. Okay? So one varies, the other varies. And if you can demonstrate that, then you're closer to establishing causality. Okay? And the last one comes back to experimental validity. Have you set up your experiment in such a way that you've eliminated all other potential causes, that you have controlled all of the other variables? That's important. Okay? So the only thing changing in your experiments are the independent and dependent variables. So these are the three things that are important for establishing causality. Like I said, I'll send it through to Bill, who'll put it up on your site. So, yeah? Okay, cool. So any questions on the stats part of it? I'll hang around to the end of the session if you have anything you want to talk to me about, but I'll pass it back to you.
Thank you very much, Sharon.
Okay.